about them step by step. However, for things that are in pure rotation, in fact, I wish I had not just erased that, because we don't do the exact same thing in 1510. So right now we in linear in 1510 in the linear direction we have relationships between velocity and acceleration. Those. So when we have things in pure rotation only, so this is rectilinear motion. Okay. And so if we have this thing called pure rotation, which something is just rotating about its center of mass, we can look at its angular things in a similar set of formulas. Okay. So angular velocity is equal to angular displacement with respect to time. Okay. Meters per second, radians per second. Angular acceleration, and again, remember this is only for pure rotation. Okay. So angular acceleration is equal to the derivative of angular velocity with respect to time in radians per second squared. And then kind of the same thing. And also radians per second squared. And we'll find that if A is equal to a constant, then we have this set of equations.
Question, isn't the bottom one on the pure rotation, isn't it dw
dx, d theta.
Yes.
Thank you. And then so in a similar fashion, then we have angular velocity is equal to initial angular velocity plus alpha t, and angular displacement can then be written in a certain form. So again, this is for if alpha is equal to a constant. Okay, constant meaning, a number, 10, 16, but like 5t would not be a constant acceleration. Okay. And then we have that other set of equations too. Okay. So, let me see. Looking back at this slide here, here's a concept question. What is the direction of the velocity of point A? If it is going counterclockwise. Yes.
Mm-hmm.
Yep, so it would be going down. If we're going the opposite direction, it would be going up. If, we'll just kind of do one step further here. So if this were at a 60-degree angle and the velocity is tangent to that, what direction would it be going? This is your 60, and this is a 90. Okay, so this velocity is going to be at a 30-degree angle. Good. So it's going to be perpendicular to the blade, and the blade is at 60, so it's at a 30. Pure rotation is so easy. Yeah. And you can also do the cross product. So we haven't done any cross products yet, but we just intuitively knew that it was in that direction. So we have that omega is going to be equal to, let's just do that this way. So it is a positive in the counterclockwise direction. So this would be 0I plus 0J plus omega k. Right? That means that the z-axis is what's spinning. Okay? The x and the y-axis are not spinning. And then we have a position vector of from O to A, and that would be minus Li plus 0J plus 0K. So if this were a three-dimensional motion, then it would be easier to take the cross product than it would be to just do the scalar analysis. Okay? So V sub A is omega cross R, and when I take that cross product, if you remember from statics, you do I, J, K, omega comes in the middle, so that would be 0, 0, omega, and minus L, 0, and 0. So do you guys extend this 2 more columns to do the cross product?
Yeah, we do it the collective way.
So you do I and J?
Yeah.
Okay. So if we do this cross product, our I components are 0. So we'll go this way. So we have 0I plus, so this should have gone, let's see. Yeah. So this would be plus omega times negative L plus 0K. Need to put my J there. And then that would be minus the opposite direction, 0I plus 0J plus 0K. Okay. A lot longer than doing it just the scalar. The scalar method, we would say that the perpendicular distance is equal to L, and omega is equal to omega. So the velocity is equal to omega times this d perpendicular, and then we just recognize that it's down. Okay? So we look at it and we're like, okay, omega is omega, d is L, and it's going to be downward. So in this scalar analysis of it, you have to think a little bit more, whereas in the vector analysis of it, when you're doing the cross product, you just have to get omega and L correct, and then your cross product tells you which direction it's in, either I or J, and it also tells you whether it's positive or negative. Okay, so if you're not good at visualizing that and recognizing what the velocity in its direction is, then you can always default back to the vector portion of it. So this slide just derives the relationships that I put over here on this sideboard. Just kind of a note here is that when we're working with two-dimensional motion, then the angular things are typically going to have k components because they're going to be spinning the z-axis. So, for example, if we have like this slab that's in the xy plane, whatever shape it may be, when it's rotating, the axis that's spinning is going to be your z-axis. Okay, so we work a lot with two-dimensional, because you can, no matter what the orientation is, you can always reorient your xy z-axis so that it's spinning in the xy plane, therefore spinning the z-axis. Okay, so we quite often our omega is only going to have a k component, as is the alpha and the theta. I could have done that a little bit shorter, but theta, omega, and alpha are typically only going to have k components unless we're truly working with a three-dimensional system. We'll do 1 or 2 of those problems, but most of the problems focus on 2D. right. So down here also, when I'm talking about acceleration, in this equation, I'm talking about tangential acceleration. When I'm talking in the linear equation, if I have an A, that's typically a tangential acceleration. So when you have something that's moving in a circular motion, I think we covered this in chapter 11, we have two types of acceleration, A sub t and A sub n. Okay? The v squared over r, or omega squared times r, and this is just dv dt. Okay? So you notice down here, we have in this acceleration, we have two terms. Okay? Which one do you think the alpha cross r is equal to, the tangential acceleration or the normal? Yes, it is the tangential. And this, when if you're doing a scalar analysis, this ends up being omega squared times r, omega cross r. Or it would be omega cross the velocity, right? Because velocity is omega cross r. So we'll kind of simplify that equation. But your velocity only has one component. Your acceleration will have two, because you are changing direction as well as possibly changing speed. And so I mentioned just a minute ago about how we typically work with these kind of slabs that are rotating in the XY plane. The z-axis is what's spinning. And so omega and alpha end up having k components. Okay? V will have x and y, and A will have x and y. And here again are the two different components. Would be alpha times r would be your tangential, and then normal would be r times omega squared. Okay, so this one's a little bit different. What is the direction of the normal acceleration? Okay, so it would be inward towards the center. And it would always be inward. Which two directions could the tangential acceleration go? Yes, so up or down depending on whether omega was speeding up or slowing down. And again, we could do that big long cross product and we would get that equation for it. Let's stop here and do a couple examples.